Okay, get this. Imagine hearing an echo, but not from something that happened a few seconds ago. I'm talking about an echo from an event that happened over 1 billion years ago. And it's not an echo of sound, it's an echo of space-time itself. Yeah, you heard that right. Today, we're going to talk about these cosmic echoes, these incredible ripples in the very fabric of reality that have traveled all the way across the universe to finally reach us.
So, let's dive in. The crazy thing is, for almost 100 years, gravitational waves weren't a discovery. They were a question, a huge question. And you know who was asking it? Albert Einstein himself. I mean, his own theory of general relativity predicted these things should exist, but even he wasn't totally sure if they were real or, just some kind of ghost in the math.
And then, it happened. September 14, 2015. We finally got an answer. We turned on what is basically the most sensitive microphone ever built by humanity, and we heard this. Just a tiny little chirp. It lasted less than a second, but that little sound, that was the universe itself, confirming one of Einstein's wildest predictions. So what was that sound, and what in the cosmos could possibly be powerful enough to create it?
All right, to really get what that chirp means, we got to go back to the beginning. We're talking about the source code of gravity, a little thing called Einstein's general relativity. And believe me, it completely rewrote the rulebook on how we thought the universe worked.
So before Einstein, right, we had Newton. And Newton's idea of gravity was pretty straightforward. It was like an invisible rope, an instant pull between two things. If the sun just disappeared, poof, Newton believed Earth would instantly fly off into space. But Einstein came along and said, hold on a second. He knew that nothing, not even gravity, can travel faster than the speed of light. So for him, gravity wasn't some instant pull. No, it was a disturbance, a ripple that actually travels through space-time.
So what this all boils down to is basically a traveling tidal force. You know how the moon's gravity creates tides here on Earth, right? It kind of stretches and squeezes the oceans. Well, a gravitational wave does the exact same thing, but to space-time itself. Now, if you were right next to the event that created it, that force would, well, it would rip you apart. But by the time these waves get to us, after traveling for billions of years, they are unbelievably faint.
The classic way to picture this, and you've probably seen it, is to imagine space-time as a big, stretched-out rubber sheet. Now, if you have something massive and it's accelerating, like two black holes spiraling into each other, they're going to create ripples in that sheet, and those are gravitational waves. But here's the key part. They don't just travel on the sheet. They are the stretching and compressing of the sheet itself. It's the fabric of reality that's getting warped.
And hey, here's a quick pro tip to sound smart at parties. We call them gravitational waves, not gravity waves. And there's a good reason for that. Turns out the name gravity wave was already taken. It's used to describe stuff like waves on the surface of the ocean, where good old gravity is the force that pulls the water back down. But what we're talking about, gravitational waves, that's a totally different beast. These are ripples in space-time itself. Big difference.
Okay, so if these waves are just these super tiny distortions of space, how in the world could we ever hope to detect them? I mean, it sounds impossible, right? Well, to do it, we had to build one of the most ridiculously precise instruments in all of human history.
And here it is. Meet LIGO. That stands for the Laser Interferometer Gravitational Wave Observatory. And you can think of it like a giant ear. But it's not designed to hear sound. It's designed to feel that tiny little squeeze and stretch of space-time as a wave passes by. And get this, there are actually 2 of them in the US, thousands of kilometers apart. And that's super important for making sure that when they detect something, it's the real deal.
So the idea behind how LIGO works is actually kind of beautiful in its simplicity, even though the machine itself is insanely complex. Okay, so here's the deal. You start with a single laser. That light gets split into 2 perfect beams. Each one shoots down a 4-kilometer-long arm, bounces off a super precise mirror at the end, and then comes back. Now here's the magic. They're set up so that when the beams meet back in the middle, they normally cancel each other out perfectly. The detector sees total darkness. But if a gravitational wave comes through, it's going to stretch one arm just a little bit and squeeze the other one. Suddenly, the 2 light beams are out of sync. They don't cancel out anymore. And that tiny little flicker of light that gets through, that is the signal. It's absolutely brilliant.
And when I say tiny, I mean it. To give you a sense of just how insane the precision is here, the change in length that LIGO can detect is about 1,000th the width of a single proton. A proton. Let me put that another way. That's like measuring the distance to the nearest star. That's Proxima Centauri, over 4 light-years away, and being accurate to within the width of a single human hair. It's completely mind-boggling. Okay, so we've got the theory from Einstein, and we've got this incredible machine, LIGO. The stage is set. So, what was it? What made those lasers flicker on that September morning? Well, the source was one of the most violent, most cataclysmic events the universe can even cook up.
This story actually begins 1.3 billion years ago. You have two massive black holes locked in this cosmic dance. As they orbited each other, they were constantly shedding energy in the form of gravitational waves, and this made them spiral closer and closer and faster and faster. And in those final insane milliseconds, they were whipping around each other at nearly half the speed of light. That's what created that rising chirp sound we heard. And then, bam, they merged into one even bigger black hole.
Look, the numbers here are they're hard to even wrap your head around. We had one black hole that was 36 times the mass of our sun. The other was 29 times the mass of our sun. So you add them up, you expect to get a new black hole that's 65 solar masses, right? Wrong. The final black hole was only 62 solar masses. So where did the other 3 suns worth of mass go? It didn't just disappear. It was converted into pure energy, an unbelievable blast of gravitational waves, all thanks to Einstein's famous E=mc². Humanity has never witnessed anything like it.
But here's the thing. This discovery, it was so much more than just proving Einstein was right again. This was about opening up a completely new window onto the cosmos.
And this, for me, is the part that really gives me goosebumps. Think about it. For all of human history, everything we've learned about the universe has come through light, right? Whether it's visible light, radio waves, X-rays, we've always been looking at the universe. But with gravitational waves, we've basically grown a new sense. We can now listen to the universe. We can hear the things that are completely dark, events that no telescope, no matter how powerful, could ever see.
And believe me, this is just the beginning. Scientists are already working on making LIGO even more sensitive. We're building more detectors all around the globe so we can pinpoint exactly where these signals are coming from. And the really cool part? There are plans for something called LISA. It's going to be a detector in space with arms millions of kilometers long. It'll be able to hear a whole different range of cosmic sounds, like the collision of the supermassive black holes that sit at the center of galaxies.
So that first chirp we heard came from 2 black holes colliding. But what else is out there? What other cosmic secrets are waiting to be heard? The explosions of giant stars? The insane density of neutron stars smashing into each other? Could we even hear the faint, lingering echo of the Big Bang itself? We have just learned how to listen, and it's pretty clear the universe has a whole symphony of stories to tell. The question isn't, can we hear it anymore? The question now is, what are we going to hear next?